Hello, Miss May. My name is Beliteda, and this is my partner Noval Dimas Azizan, and we want to present our research titled Comparative Analysis of Piezoelectric and MPU6050 Sensor Performance in Detecting Earthquake Indications. So, let's jump into it. Why we choose this topic? Earthquake usually occur in Indonesia, and until now, earthquake is cannot be predicted accurately. And current technology in Indonesia only provide information after an earthquake occurs. From that condition, we want to do a research an Arduino sensor like MPU6050 and piezoelectric to be a budget-friendly earthquake early warning system or EEW. Why MPU6050 and piezoelectric? MPU6050 is a digital sensor that detecting three axes using gyroscope, and piezoelectric is an analog sensor that detecting vibrations. Okay, let's jump into literature review. In this section, we take reference from two papers where they use ESP8266 as a microcontrollers and a sensor that ensure there is vibration or not, namely SW420 and also piezoelectric sensor, and they also divide into three categories, namely safe, alert, and danger. And also from the result of their experiments, they success in classifying that use voltage of 0.039 volt or ADCA is classified as safe, while 0.195 volt or ADC40 is considered danger. And they're also using buzzer and LCD display for local notification and remote notification using Blink. And there is also paper that discuss using ESP32 and MPU6050 sensor. The MPU6050 sensor is offering higher precision by measuring acceleration on three axes, and they achieve an accuracy rate of 96%. And this study compares a piezoelectric sensor and the MPU6050 for detecting earthquake indications, focusing on sensor sensitivity and vibration reading accuracy. The piezoelectric sensor detects analog to digital conversion or ADC values generated by physical vibration, while the MPU6050 measures three-axis acceleration, later processed into magnitude readings. Both sensors were tested under identical simulated vibration conditions. Performance evolution was based on ADC values for the piezoelectric sensor and magnitude level for the MPU6050 as the primary indicators. Next, to methodologies. Our research workflow consists of system design and prototype development, functional testing, test scenario design, and data processing and analysis, and finally, performance, evaluation, and comparisons. This is our flowchart showing how the sensor reads the input, transmits the data, and produce the output. Same only convert to block diagram. And next, this is our schematic design for piezo and NPU6050. And for the functional testing, here we just make sure that all our sensor and microcontrollers can run. And next, for test scenario design, we divide the test into three categories: safe for 2 kilogram, or for 4 kilogram, and danger for 6 kilogram. Like paper before. For each category, a load of 2 kilogram, 4 kilogram, and 6 kilogram was dropped from high of 15 centimeter, 30 centimeter, and 45 centimeter. Each test condition was repeated 5 times, 5, to ensure consistent and reliable results. Okay, next, this is our tools. As you can see, MPU6050, Piezoelectric, and ESP8266 here in the box. And we'll drop each weight right on top of these things. Next, after doing some experiments, we get this value. This table shows the peak value from every we drop the load from the piezoelectric output, which is ADC value. As mentioned before, we must convert this value into label, but before convert into labels, ADC values must be converted into MMI scale first. MMI scale is a scale to measure how fatal the impacts on earthquake have occurred. This table shows the peak value from every we drop the load from MPU6050 that output the magnitude. After that, we convert the magnitude from MPU6050 into labels with the threshold we got on
from other paper. Every value less than 3 will labels with safe and so on. Same like before, we convert into labels, but the threshold is different. We get this MMI scale table from other research and we categorize this table into our labels. Every MMI value that less than 5 is converted into safe labels and so on. We want to calculate how accurate the sensor is detecting labels from its category, like how many safe label is detected from 2 kilograms or safe categories. In this case, safe is detected in piezoelectric is 11. So the accuracy is 11, but divided by total experiment is carried out, which is 15. Other levels is applied, same calculating accuracy methods like the safe labels.
Next, for result and discussion of the accuracy and the sensitivity. Okay. For the accuracy, the result of piezoelectric get 73.33% for safe and 6.67 for alert and 6.67 for dangers. And for MP6050, we can see 20% for safe, 27% for alert, and 0% for dangers. And for the sensitivity, we can see the advantage of piezoelectric is much more sensitivity to small vibration, and disadvantage is after the peak, it immediately drops to zero. This means that adaptation is fast, but the baseline is less stable. And we can see for the advantage of MPU6050 is high stability before and after the incidents. And disadvantage is the sensitivity is lower. If the vibration is small, this means the sensor is superior because its baseline is clean and its return to stability quickly.
Lastly, the conclusion and future roles. The piezoelectric sensors perform more effective than the MPU6050 in detecting earthquake indication, especially for small vibrations, while the MPU6050 offered better baseline stability for significant events. The challenge is the container used in the experiment where its construction was not fully optimal for supporting relatively heavy loads. This condition could potentially affect the stability during measurements, leading to slight variations in the results we got. For the future works, sensor fusion approach integrating piezoelectric sensor for early detection and MPU 6050 for peak monitoring. And hence with machine learning is recommended to improve accuracy and stability in real life earthquake scenarios. And thank
Thank
you.
you.